Hello from the Design Automation Conference 19 in Las Vegas. I'm very happy for the next interview because, first of all, I am interviewing the general chair of DAC, so you know, a very important person. And in addition, it's Rob Aitken, who is a fellow from ARM, so I am very honored. I have the general chair with me and the ARM fellow. And number 3, I'm very excited about the topic because it had something to do with wafer scale integration. And guess what? In my life, I've written a book on wafer scale, and I tried some wafer scale integration with STMicroelectronics. So I was so surprised that this topic comes back. So Rob, I am more than happy to listen to you.
Excellent. Thank you very much, Gabrielle. Yeah, I picked the topic of wafer scale integration precisely because I remember a FTCS back many years ago that I attended, and you were speaking and giving an excellent lecture on wafer scale integration. And it's interesting because it was around the same time that the second wave of neural networks was happening, and I was doing some work on those as well back in those days, and it was kind of like, oh yeah, this is all exciting. And then it hit various problems. Wafer scale integration hit the challenge of making things yield, and neural nets hit the challenge of not having enough iterations of Moore's law to process them. But it was I thought it was a good topic to come back to, because when you look at the industry and think, what are we going to do in the post-Moore phase? We've had a couple of discussions so far that at DAC that essentially say, well, the next generation is up. We're going to start integrating things vertically, and if you look at, say, a lot of memory modules or vertical NAND, these kind of things are already taking advantage of 3D integration. And when you look at the high-performance compute community, they're looking at that and saying, let's assume the vertical integration of various sorts is a done deal. Now, the next question is, okay, where do we go from there? And what they're thinking is maybe we can move out from the tyranny of how much you can fit in a reticle and start building bigger silicon objects. And so there was some recent work done between University of Illinois and UCLA on what they're calling wafer scale again. And it's a slightly different approach than was done in the past, but they're taking the observation of, if we can build an intelligent, flexible interconnect substrate, and then we can build some copper pillars on top of that and attach individual GPU die and attach individual memory die and so on, and build what amounts to a 3D integrated, relatively large-scale area object, can we use that to improve computation? And they did some silicon experiments to demonstrate that the pillar structure works and that they can get that to yield. And they did some experiments, simulation experiments, to determine what the optimal number of GPUs was to put on such an object in order to satisfy yield and manufacturability at existing levels, but also to obtain a performance advantage over where you can achieve now with, say, 4 GPUs on an MCM. So they compared a 40 GPU monolithic object with 10 4 GPU MCMs cooperating together. And they concluded that the 40 object had about a 5x performance advantage on the average case and about a 20x performance advantage in the best case, and is able to do that at significantly lower power than the classic multi-chip module approach, and that's mostly due to savings in the I/O. So it's an example of an old area coming back.
Yeah. Okay, I think this is the most exciting video I have made during DAC. So I hope I will hear again next year and the next coming year. If it really gives the expected result, we'll see.
Very good.
Anyway, thank you very much.
Thank you.